chapter 5, which is about counting principles. We have learned about permutations and combinations. Do you still remember the difference between permutation and combination? Anybody? You can write in the chat section, or you can just say it out loud. What is the difference between permutations and combinations? Unsure? Nobody wants to try? If you're shy, you can just write in the meeting chat. So anybody, you can write it here, or you can say it out loud. Nobody knows the difference. Okay, Muhammad Farhan. Permutations are used when order or sequence of arrangement is needed. Combinations are used to find the number of possible groups which can be formed. Okay, the keyword here is permutation requires order. Combination, no need order, just any combination. All right, so that's a, yeah, right, Farhan, but I just put it in one simple word, order. Permutation counts the order, combination does not. So maybe I'll give an example. A, B, B, A are considered 2 permutation. Now, on the other hand, combination, for combination, AB or BA is considered only 1 combination. Because you see, the order is not important. As long as AB, BA, as long as AB or BA. Let me give you an analogy. You go to the mama restaurant. You order roti canai and teh tarik. Does it make any difference if you order teh tarik and roti canai? Whether the roti canai comes first or teh tarik comes first, does it make any difference? No, right? That is called combination. Now, let's say from this class, I need to choose number 1 student, number 2 student, and number 3 student. Number 1 with the highest score, second with the second highest score, third with the third highest score, for example, from the test 1. So is that combination or permutation? Definitely it's permutation, right? Because if I say Adam is number 1, Eve is number 2, Lily is number 3, definitely it's not the same as Lily number 1, Adam number 2, Eve number 3. Not the same because the order is different. That is called permutations. That is considered 2 different permutations, but same combination. Do you get it? So I hope at this point of time it is crystal clear in your mind. Now, permutation and combination can be used with or without repetition. Does anybody still remember or not? What is meant by repetition? Permutation can have repetition and without repetition. Combination can also be with or without repetition. So what is meant by repetition here? From the previous lecture, I already given one example, right? before I give the answer? Yeah, please.
The sec number.
Yes, Stephanie.
That day you said like if you take the number and then we put inside the sec bag, that is repetition.
Yes, yes, that's called repetition. You see, remember the sack. There's one sack, and inside the sack there are 10 digits: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. After I take it out, the first number, if I don't put back, no repetition. If I put back, so that the second time I pull from the bag the same number of 10 digits, that is called repetition, because I put back. So there is a chance that the second time I pull out, there is a possibility that the same number will appear again. Correct or not? If repetition is allowed. If repetition is not allowed, no repetition, from the sack, I take out one number already. I don't put back. So when I pull the second number from the same sack, let's say the first number is number 5. So if I pull the second number from the sack, is it possible to get number 5 again? Is there a possibility at all? The answer is no, because there's no repetition. I already taken out the number. Whereas in the case where repetition is allowed, we put back that number so that the second time we randomly take out one number, there's still a possibility to pick back the same number. That is what we mean by repetition. Yeah. Okay. Another thing, before I continue with the lecture, I want to point out a few things that I think some students may need some clarification. Factorial. So if I ask you factorial 5, this is factorial 5, right?
Yes.
Okay, let me see if I can make it larger a bit on the screen. So factorial 5 means, oh, cancel, sorry. 5 times 4 times 3 times 2 times 1. Is there a possibility times 0? Of course, no, because anything that times 0 will give you 0, right? So we don't times 0. So it's 5 times 4 times 3 times 2 times 1. So it's descending. Now, if I give you another number, let's say 4 factorial. Then this is equivalent to 4 times 3 times 2 times 1, right? Now, let me ask you, let me show you something. If I take 5 factorial, divide by 4 factorial, what do you think is the answer? Now, some students may do like this, right? Some students may do like this. Not wrong, not wrong. But do you notice that 4321, 4321 is the same here? We can cancel out this 4321 divided by 4321, right? Correct or not? So the answer is what? 5, correct? This sounds like nothing like, this is like common sense, isn't it? But let's say so, gentlemen, what's the answer? Ladies and gentlemen, what is the answer for this? I'm going to take calculator out and count one by one. Correct. No, I did right. Correct. 200, right? How do you know? Because you see, 200 factorial means 200 times 199 times 198 times so on and so on until times 1, right? And then 199 factorial is equivalent to 199, 198, 197, right? So you see the 199 from the top here can be cancelled out by this 199. So you don't need already. Now, maybe it's hard to show by example using this, but look at this one. If you get this idea, you understand this idea. You get this idea or not? The rest of you. Who does not get it? Raise your hand. I will repeat again. If no, I assume that everybody understands it perfectly. I will move on. Perfect lah. Okay, thumbs up means perfect lah. Huh? Now, let me give you another example. 5 factorial divided by 3 factorial. What's the answer? Now, you can do the hard way by writing something like this. Yeah, you can do the hard way. Yeah, you can do the hard way like this. Or, I would say that you straight away write 5 times 4, and then you stop at 3 already. 3 no need to write. Because why? It has been cancelled out by 3 factorial. So, the answer is 20. So this may seem trivial, nothing that useful or important. But when you do permutation and combination, right, using very big numbers, let's say 211 factorial, let's say 208 factorial. If you understand the concept perfectly, you simply take 211 multiplies 2110 multiplies 209. That's it. You multiply this, that is already the answer. Yeah. So if you understand this concept, so this is just a recap of some of the important things that I hope all of you are crystal clear about. So there are formulas where there are formulas for permutations, there are formulas for combinations, there are formula for combinations with repetition, and also there are formula for combinations without repetition. Like this K combination, no repetition. This formula, no repetition, K combination. The other type is called K multi-combination. This one allows repetition. And you see the formula is actually similar to K combination. It's quite similar to this. You see? It's quite similar to this. The only difference is what? For K multi-combination, you see the brackets, double bracket, right? And then if you want to remove the outer bracket, what you need to do? The top there, you need to take the n plus k minus 1. Then but this second part is just a normal K combination. This second part is just a normal K combination. All right? So roughly, that's about it for counting in permutation and combination with and without repetition. The last section of this chapter is on the pigeonhole principle. The pigeonhole principle is an idea, it's a mathematical idea based on logic. Yeah, you see, imagine there is a shelf. In the shelf, there are 9 pigeonholes. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, in the olden days, people used pigeon to send letters. In the olden days, for postage, right? They used pigeon to send letters. So what happened is that they will tie a small piece of note on one of the pigeon's feet, and then they free it. All right. So the pigeon will fly to another pigeonhole, and then another day the pigeonhole will fly back to the first pigeonhole. So that's how they use the pigeon to exchange or to send letters in the very olden days. Yeah, before telegraphy, before there was internet. No, before there were this normal mail around. Now, let's say that we have 9 pigeonhole, but we have more than 9 pigeons. Okay, we have 9 pigeonholes, but we have more than 9 pigeons. So what will happen is that, let's say, if we have 10 pigeons, definitely one of the pigeonhole we have 2. One of the pigeonhole will definitely have 2 pigeons, correct or not? Randomly lah, any one of the pigeonholes might have more than 1 pigeon, might have 2 pigeons, correct or not? So that is the concept, yeah. That is the concept. Now the assumption is that we need to distribute the pigeons evenly, you know? But by nature, the pigeons, no pigeon will leave the pigeonhole empty, you know? They try to occupy it, and of course, they may not want to share with other pigeons unless it is forced to. So I've shared the YouTube videos explaining pigeonhole, and also another YouTube video on applications of pigeonhole. Yeah. Pigeonhole concept or pigeonhole principle is used for resource planning. Okay, such as distributing n items into m groups. You know, construction planning, lossless data compression. Okay, so let's look at another form of the pigeonhole principle. This time using Venn diagram. Now, suppose that we have 2 finite sets here. The first set is called X. The second set is called Y. Yeah. And then in set X, there are 5 elements, and the elements are 1, 2, 3, 4, 5. In set Y, there are 3 elements, which are A, B, and C. Suppose that there is a function. Remember relation? Yeah. Function allows relation to occur. Function maps different sets together. So there's a function that maps X to Y, whereby X is the domain set, Y is the codomain set. Function maps domain to codomain. In this case, the domain is set X, the codomain is set Y. All right. So when the mapping occurs, yeah, if the domain is bigger than the codomain, if the domain is bigger than the codomain, okay, there is a possibility that some of the elements in set X, yeah, X1, X2, X3, X4, X5, some of the elements in set X may be sharing the same mapping. In this case, it mentioned here that element X1 shares the same mapping with element X2, whereby element X1 and X2 belong to the same set X. See, please follow how I read this. Whereby both elements are not the same. So this is the second form of how you can write the pigeonhole principle. When does this occur? This occurs when there is a mapping from a bigger domain to codomain. Now, if you think about this, right, you try to relate to the pigeonhole. Which one is resembling the pigeon? Which one is resembling the pigeonhole? X is pigeon or pigeonhole? X is pigeon or pigeonhole?
Pigeonhole.
Try again. Try again. Definitely the answer is a pigeon, right? Not. Yeah. The X is pigeons, because the pigeons need to fly back to the pigeonhole, and there's not enough pigeonhole. So some of the pigeons need to share pigeonhole. So Y is the pigeonhole, X is the pigeon. So you see, pigeon number 1 and pigeon number 3 has to share the same hole. Pigeon number 2 and pigeon number 5 has to share the same hole. Pigeon number 4 is lucky lah, because nobody is residing in that hole. So pigeon number 4 has that hole B all for itself. Yeah. Because you see, if you look at the pigeon, right, naturally when imagine if you're a pigeon, would you go to any hole with other pigeon already? Definitely you won't, right? You fill up the holes without pigeon, first, until all the holes are taken up. Then you have no choice. If you are the late pigeon, then no choice. You have to choose one of the existing holes already with a pigeon. Okay, so this problem is always seen when we are doing mapping, whereby some of the domain elements will be mapped to the same codomain as resembled here. See, x1, x2 does not mean x1 does not mean it's number one, x2 does not mean number two. You know, the first element and the second element does not mean the first element and second element. It means two different elements of the same x may share the same mapping. You see, f x1 is the mapping, x1 is the element, f x2 is the mapping, x2 is the element. All right. No Urwani or share her answer in the chat, which is pigeon. Yeah, that's correct. So don't be shy to try. Last time as a student, I always make mistakes. Nobody remembers that. Yeah, I said myself. So you shouldn't be worried about making mistake. Okay, the third form of pigeonhole principle. Let's try to read this together. If x and y are finite sets, okay. So finite sets means the number of elements inside them are limited lah. They won't become infinite, limited lah. With the cardinality of x, remember this symbol means cardinality. How many members? The number of members in x is n, and the number of members inside y is m. Okay, n here is given by n divided by m. Then there are at least k values a1, a2 to ak element of x such that the mapping of a1 of any a1, a2, the mapping of any of the elements inside x may be similar. So in this case, we have more than two domain elements which are mapped to the same core domain. You see, F means mapping. A1 is the element. So A1 and A2, both elements from the first set X are sharing the same mapping. Yeah. And in this third form,
Sir, I think you're muted.
oh, how long have I been muted?
Maybe for a few seconds ago.
Okay, when I was here, was I muted yet? Because I do not know how I get muted. I didn't mute it, actually. Was I muted here? Since here?
No.
It's only when I'm here, I got muted.
Yep.
Now, when I was explaining the purpose of n divided m, was I already muted?
Yes, I guess.
Okay, then I repeat this whole slide again. I repeat this
Okay.
whole slide again.
Okay.
Okay, so we have the first form. The first form says that if more pigeons than the whole, so some pigeons have to share. That's first form. Second form is we are representing it in the form of a Venn diagram. Yeah. So for two, there may be two members from the domain that needs to share the codomain, that needs to share the mapping. Now, in the third form, it says that they can be more than two. Yeah, it can be more than two which share the same mapping. In this example, you see here, what element 1 and element 3 sharing A, element 2 and element 5 sharing C. Element 4 is lucky lah. It has B for itself lah. No need to share. Okay. So is there a way for us to predict how many will be sharing in the domain, in the codomain? The answer is very easy. Number one, inside the first set, yeah, the domain set, you count how many elements. How many are there? 5 elements, right? So let's say n is the number of elements inside set X. So it's 5 elements. And then m is the number of elements inside set Y. So how many elements are there? 1, 2, 3, right? So if we follow this third form formula, right? We take n divided by m. So we are taking 5 divided by 3, right? 5 divided by 3 will be 1.6666, isn't it? 1.66666. So we don't care. We would just want the ceiling. 1.66, we take the ceiling. We don't take the floor. 1.66 floor is 1. 1.666 ceiling is 2, right? How do you know it's taking the ceiling? You look at this notation. It looks like a bracket, right? But it's incomplete bracket, right? So we take the ceiling of 5 divided by 3. The ceiling of 1.666 give us 2. So you see, the K here is showing us the number of sharing. So the number of sharing here is, some of the mapping we have, maximum 2. Now, if I go back to this example, okay. Now let's say there are 6, 1, 2, 3, 4, 5, 6. So there are 9 pigeonholes. I'm trying to show you how to use the third form. Let's say there are 9 pigeonholes, and there are 9 birds. 9 pigeons, 9 pigeonhole. So using the third form, K, we take n divided by m, right? The number of pigeon is 9. The number of hole is 9. So 9 divided 9 is 1, right? So one hole will have how many? Maximum? 1 only lah. 9 divided by 9, isn't it? Let's say now we have a 10 pigeon. We have 10 pigeon. 10 pigeon. And we have 9 holes. So just now, if we take the formula from the third form, yeah, n is 9, n is n is 10, m is 9, right? So you see, n is 10, m is 9. So max sharing is given by K which is n divided by m Okay, I cannot write the symbol here, so I will just put bracket there, ceiling. I take the ceiling. So the ceiling of 10 divided by 9 will be 1.1111 something, right? So we take the ceiling, which is 2. So you see here, there are 2 birds here, right? Maximum sharing will be 2. Now, suppose that, suppose now let's say there are 21 pigeons. Still the same number of holes. So how many maximum number of pigeons in a hole now? Are you able to count? (21) divided by 9. So let's take out the calculator. Maybe you want to try along. If you try, you won't be sleepy. If you don't try, you'll be sleepy after listening sometime. Mathematics requires you to do the thinking. If you're just listening, you fall asleep. 2.333. 2.333. Which will give us what? We take the ceiling, we're not taking the floor, right? This is not rounding up or rounding down. Ceiling is rounding up. So maximum sharing will be 3. All right. So I just going to put here. Maybe I will put this in my Facebook group. Yeah, put in Facebook group so that at least you have a note on this. But still, it's good for you when you study, you try to make your own note, even though I sometimes provide the notes. Because when you write notes, you tend to be engaged and be more active in studying. But of course, if you spend too much on writing beautiful notes, like rather than listening and joining the discussion, then you may be losing instead of gaining. Okay, so let's look at one example. Prove that if 6 integers are selected from the following set. This set has what element? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. How many elements are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 elements. Yeah, there are 10 elements. I want to select 6 from the 10 elements. Yeah, I want to select 6 from the 10 elements. And from the 6 integers selected, right, there must be 2 integers whereby after we combine them, we add them, the sum is 15. All right. So this is how we're going to do it. We pick up the 6 integers, right? We're going to squeeze the 6 integers into 5 boxes. When we squeeze the 6 integers into 5 boxes, definitely one of the boxes will have 2 integers lah. Okay. So by pigeonhole principle, one of the boxes holds at least 2 integers. There must be 2 integers that sum to 15. Okay, so here you can try 10, 5, 15, 9, 6, 15, 7, 8, 15. Okay, 4, 11, 15, 3, 12, 15. So that's how you do the analysis. All right. So to see how this is being worked out, you can look at this YouTube video, which I share at the bottom of the slide. Okay, so I don't want to spend too much time on Pigeonhole because this is just for you to know. Yeah, I don't intend to ask this in tests, nor quiz, nor final exam. It's just for you to know because it's in the syllabus. So we are done with chapter 5 counting, whereby we have learned the basic counting principles. Yeah. So what are the 2 principles? One is multiplication, the other is adding, right? Yeah, one is adding, one is multiplication. Example of multiplication. For example, there are 3 types of pizza and 2 types of drinks. So somebody, a customer who comes to the pizza parlor will select 1 pizza and select 1 drink. There are 3 types of pizza, 2 types of drink. So how many possible ways of selecting different pizza and drink? So we can use a multiplication principle. Yeah, multiplication principle, whereby we take 3, multiply with 2. So there are 6 possible combinations. Now, can we use a combination for this? The answer is yes. We can use combination. Not just a rule of multiplication, we can also use combination. Because we just need to find combination of 1 pizza and 1 drink. The answer will be the same. The answer is definitely the same. Yeah. So you don't believe? Okay, let's try it. Let me go back to the Jamboard. Okay, let me write something here. Pizza, a customer orders one pizza and one drink. The restaurant or cafe has 3 different pizza types and 2 different drink types. What is the possible number of different ways a customer can order? Okay, answer. Use multiplication principle. If you remember multiplication principle from a very first one, multiplication principle. All right. So multiplication principle says what? So we just multiply. Yeah. We just multiply. The first choice multiply with second choice multiply with third choice. Then we'll be able to find the possible number of choices. All right. So with multiplication principle, three types of pizza times 2 types of drinks. So it'll be 6, right? Or use combinations. So what's the combination formula? The combination formula is NCR, right? From NCR. Here, can we use NCR? Let me see. Not really, because 2 different types of things. Not really. We cannot use combination, but we use multiplication principle. Yeah, we cannot use combination here. All right. So that's it. That's what is multiplication principle. There are times when we can use both, but in this case, I cannot use combination formula, because for combination formula is like this, NCR, whereby we choose selected number from possible total combination, but NCR is not suitable in this case. It's better to use a multiplication principle. All right. We have learned about we have also learned about arrangement using K combination. And if we have repetition, it's called K multi-combination. If the order is important, if the order of the if the order, i.e. the arrangement is important, then it's called permutation. So the formula for permutation and combination is quite similar also. So the difference is what? No? Permutation, you further divide one more figure. Let me see what's permutation. You see, permutation you use P and K, not C and K, whereby n factorial. Just now, if you're using combination, right, n factorial divided by K factorial. Yeah, but in sorry, if combination, we take n factor divided by K factorial divided by n minus K factorial. But if permutation, you just take n factorial divided by n minus K factorial. Okay, you just compare the formula. N factorial divided by n minus K factorial. You see, combination is how? See, combination n factorial divided n minus K factorial, quite similar, right? Except if further divide by K factorial. Usually there'll be less number of combination compared to permutation. Usually less. Yeah, because A, B, B, A, there are 2 permutation, but if it's a combination, it's only 1. So it's less. So I hope you're following. If you do some exercises, then only probably understand. This thing is actually already taught in additional maths and modern maths last time. Perhaps this is a revision for some of you. Perhaps some of you that actually have not been exposed as thoroughly, then perhaps you need to revise this back. All right. And then we have also looked at pigeonhole principle in problem solving, whereby we are trying to map more to less. When we map more to less, then some of the more elements in the domain will be paired up, will be sharing the same mapping. Any question on counting before I move on to probability? Okay, I see one question from Dashni. So, basically we tambah one, kan? Which one are you referring to? Oh, you are referring to the pigeonhole principle, right?
Yes, sir.
Okay, not necessary add one, not necessary add one. I think you made this conclusion because you were assuming that you're looking at this example, right? Not that's why you assume just to add one. Not necessary. Not necessary.
I think it's the formula, the third
Use this
formula.
formula. The third form formula, is it? Then I give you two examples already, right? When we have 10 pigeons, 9 holes, then the maximum is 9. Maximum is 2. I like illustrated here lah. But
Okay.
when sorry. But when we have 21 pigeons, still the same number of holes, then we use the formula, you see, it's becoming 3. So some of the holes we have 3 pigeons.
Okay, sir.